Okay, so okay, let's continue. Okay, so previously in the first half of the workshop, you have seen algorithm analysis, right? Using big O notation. We have seen many different types of growth rate using the big O notation. And what it means, if let's say when you analyze your algorithm and you find that your big O is order of n, and your another algorithm, the big O is order n power 2. So from there, from the big O notation only, then you can actually compare which algorithm is more efficient when the data size increase. Okay, then you can select which one you want to use so that your algorithm is more efficient. Okay, when it solve the problem that you want. Okay, and now let's look into searching, different types of searching method. Okay, that you can use when you want to perform searching. Okay, so why do we need to learn this searching, right? Actually, searching is one of the important tasks in computer science. Okay, because nowadays you know that there are a lot of information, right? Okay, out there, and to retrieve the information proficiently, you actually need a very efficient searching algorithms. Okay, if not, it will be very slow when you want to find something, right? Okay, and there are certain ways that we can organize the data that can improve the searching process, right? Just like that's why you need to learn what is data structure so that you can structure the data, right? Then if you want to keep this data in proper order, so that it's easy to search later, right? Okay. Now let's look at what are some of the searching algorithms that you can use when you want to search for something. Okay. Here we are going to learn linear search, binary search, and also a type of storing information called hash table. Okay. Okay, let's look at the first searching method. We call it as linear search. So this linear search, sometimes when you search what is linear search, right? They also call it as sequential search. Okay, it is actually the most basic searching algorithm that you can use. I think this one you should know how to use already. For example, now given to you an array like this one here, then you want to find a value in this array. For example, you want to find -5 in this array, right? You want to know where it is stored in the array. So how do you do that? Okay, it's very simple. You just have to go through each element in the array, starting from the first one, right? Okay, you start from the first one, and then you just compare, you take out the element in the first index here and compare with your target, means the value you want to find, this -5. Are they the same? If they are the same, means you found it, right? You found, oh, -5 is in index 0, for example. Okay, if it's not the same, means, oh, this is not -5, not what I'm searching for, not your target. Then what you do, you just move to the next element in your array, the second one. And then you take the second element here and compare with your target again, and to see whether is it the target value. If not, then you just move to the next one, right? And then now when we are in the third one, then you found already, right? When you found, oh, this is my target value is -5, it's the same as my target. Then what we do, you return the index of this target value. It's like where it is stored, in which element this target value is stored in this array. You should return 2. Index 2 means the third element, right? So this is linear search, a very basic searching method, right? And this linear search is very useful if you use it for unsorted array and your array is small. Like this one, we just have 7 elements. Okay, if I want to search for anything, I just use linear search because it's very simple, right, to execute. Okay, and this is the code to perform linear search. As you can see here, we just pass in the array, the size of array, and the target value, the items that we are searching. So in this algorithm, I just need one loop that will go through every element in the array. Okay, starting from 0 until size -1 actually. Okay, Every time I will just compare whether the current element array I, is it the same value as my target value? If it's the same means I found, then I straight away return I. Then I won't stop, continue to search for whatever is left in the array if I haven't finished searching everything, right? And if not, then I will go to the next I and then continue to compare only. Okay, if let's say this item doesn't exist, the target that I'm searching doesn't exist. Okay, for example, for this one, if I'm searching for value 10, as we can see here, 10 doesn't exist, right? So what should we do? So here, if let's say you go through each element in, let's say you execute fully the for loop, starting from 0 until n-1, you also cannot find array I equals to target, right? So you won't return anything in the for loop. Then you will terminate the for loop, right? Finally, because you have searched everything in your array. Then finally, what you do, the last return here is -1. So when you call this linear search, if the value returned back is -1, you know that the target that you are searching doesn't exist. Okay, else it will return the index value of where your target is stored in the array. Okay, so it's a very simple algorithm, linear search, the most basic searching algorithm that you can use, right? But then this linear search you see, in terms of best case scenario, it will be order of 1, right? Because if the first item that you are comparing is your target, then you compare 1 only. Best case, right? You perform the minimum step. The first element is your target. But worst case means it doesn't exist, right? You have to compare all. So it will be order of n because you have 1 for loop. Okay, average will be somewhere in the middle between your 1 and order of n. Okay, means that your target is somewhere in the middle of the array. Okay. Okay, now if we talk about the worst case scenario for linear search, is order of n. Okay, let's look at our second searching algorithm. Okay, another searching algorithm, this one is called binary search. Okay, so binary search, when you want to perform binary search, right, there are some conditions that you need to fulfill first before you can apply. The first one is the list or the array that you want to sort, that you want to search, it must be a sorted array or a sorted list if you apply to list. Okay. Then if possible, you can use random access. Okay, it will be easier because we will because for this search, you are going to search a certain area in the list or the array. Okay, that's why if you can use random access, it will be better. If not, it is quite difficult to apply. Okay, then here you can see that the array that we use to perform this binary search, right, is a sorted array. If it's not sorted, it cannot work. Okay, for binary search, okay, remember this. For linear search, if it's not sorted, it still can work, but binary search cannot. Your array must be sorted. Okay, then this binary search is actually very similar to the binary search tree search that you have seen in your second workshop when you learn what is binary search tree, right? And then you learn if I want to search for any item in my BST, the binary search tree, remember what is the step? Like just now I also mentioned in our first half of the workshop, you always will select either go to left or right to search for this item, right? Okay, so let's see how binary search is similar to this BST search. Okay, here I will show you the array implementation of this binary BST search, so that you can understand clearer about what is this binary search, because you can see the name is quite similar, right? This is binary search and that one is binary search tree search. Okay, so okay, given this binary search tree, okay, this tree is a binary search tree because as you can see, how do we arrange the data when we build this tree, right? If the root is H, everything here in the left subtree of your H must contain value less than H, right? And everything on the right subtree of the H must contain value more than or it can be equals to H here on the right hand side, right? For every node also you follow the same rule. Like D, everything on the left must contain value less than D, and everything on the right here must contain value more than or can be equal to D, right? So if each node in your BST follow this rule, then this is a BST, right? Okay. So the thing is, if you traverse this BST using in-order traversal, there are three traversal methods, pre-order, in-order, and post-order, right? So if you use in-order traversal to traverse a BST, the order that you get, it's like which node you will process first will be in ascending order, right? This one you should know already last time. So if I traverse this BST using in-order and I store the value that I process in an array, this is what I get. It will be in ascending order, A, B, C, D, E, F, G until O, right? You can try yourself. Okay, so this is my in-order traversal of this tree. I store it in an array. Now, okay, so let's see. So this new representation is like, because I want to show you how the binary search is similar to the BST search here. That's why I will traverse this BST in order and then I put it in the array. Okay. And also it works well if you don't add node or also delete node to your BST, of course. Okay, so let's look at this one. Okay, we look at just to refresh your memory. How do we actually search for an item in a BST? For example, based on this BST, if I want to search for G, how do I search for G? Okay, the searching will start from the root, right? You will compare this G, means that your target value is G, compare with the root. And then you find that, oh, this root item is not my target. It's not G, right? Okay, it doesn't matter. Then I have to decide, should I go to left or should I go to right of H to look for G? Right. So based on our BST rule, G, if it exists in this BST, it should be on the left-hand side of H here. But I don't know where, but it should be on the left, right? Because the rule is everything less than H should be stored on the left. Okay, and G is less than H in alphabetical order. So I will go to the left-hand side of H to look for my G. And I can totally ignore the right-hand side, right? I don't have to come here. I don't have to waste my time. I go to the right-hand side of H to look for G because it won't be there. It's based on the BST rule. Okay, so I will just go to the left-hand side of H. Just concentrate here to look for my G. Then the next node that I'm going to compare will be this left-hand side node of H, which is D here. And I find that, oh, this is also not G, not my target value. It doesn't matter. Then I just have to decide, should I go to left of D to look for G or go to right of D to look for G? So based on alphabetical order, G is bigger than D, right? It should be on the right-hand side of D. Then I can ignore the left-hand side of D. This part, I don't have to come here. I just go to the right-hand side of D. So the right-hand side of D, it will be F. So the next node that I'm going to compare with the target value will be F. But it's still not G, right? But doesn't matter. I just decide, should I go to left or go to right of F to look for G? Based on alphabetical order, G should be on the right-hand side of F. So I will go to the right-hand side of F to look for G, and the left-hand side here, I can totally ignore. I don't have to come to the left-hand side of F. Okay? And then the next one that I'm going to compare with will be the node on the right-hand side of F, right? Which is actually G. So when I compare with my target value G, it's the same. So I finally find my target value on the right-hand side here, right? Okay. So this is how we look for an item in a BST, right? Okay. And here you see, one thing good about this searching for item in BST is it only travels one external path. Means that every time it will just come to here and then decide, okay, go left or right or go left. Then come to here, oh, this is not target, then go left or right or go right. It will select either left or right to go until you find or until finally you cannot find out, okay, the item that you are searching for. But you only traverse one external path. It's like the comparison you need to do to find the item is actually much less compared to if I tell you that this is not a BST, it's a BT. Remember binary tree? Binary tree, there is no arrangement one. You can simply put any node value anywhere that you want. So if that is the case, you have to search one by one. It's like you have to search every node basically to compare until you can find. But this one, you don't have to, okay? So our binary search is similar to our binary search tree search, where you don't have to compare every node like the linear search. Remember linear search just now? You have to compare one by one until you can find, right? So linear search is similar to if you are searching for something in a normal binary tree, where no node arrangement. Your array, like in linear search, is not sorted, right? That's why we have to compare one by one until you can find. But for binary search, you don't have to do that. Your array is sorted, so you will follow the same concept on how you find an item in a BST in a binary search. Okay, so let's see. So this is how we find item in binary search tree, right? So now let's say for binary search, now we look at binary search. For example, this is my array. This array, the content is similar to if I traverse this BST in an in-order traversal, right? You will get the value in ascending order, okay? So here also, I want to search for G. It's like here you can see that the value is sorted because it's in ascending in alphabetical order. I want to search for G using binary search. How do I perform binary search? You see, it's similar to how just now I search for G in the BST. Okay, to do binary search, you need 3 variables: start, mid, and end. Okay, when you start, right, this start and end, these 2 variables is like to how to say, to determine the boundary or where you are going to search in the array. So when you just start, right, your start, the value will be 0, means index 0. Your end will be the size, the last index value in your array, 14. Okay? Okay, and the mid, okay, what is this mid? This mid is like you need to find, okay, between your start and end, the middle element. Which one is the middle element? If your start is here, your end is here, your middle should be somewhere between the middle of your start and end. Okay, so how do I calculate the middle? You just use the formula start plus end divided by 2. So here your start initially when you start to search, start will be 0, end is the last index 14. So 0 plus 14 divided to 7. So your mid is the element in index 7 in your array, which will be H. Similar to this BST, the first one you check is H, right? Okay, so what you do? What you do is you are going to every time based on the middle element, you will take this middle element, compare with your target. My target is G, right? I want to search for G. Then when you compare H and G, it's not the target, right? H is not the target. Okay, but never mind. Then, okay, H is not the target, but if this G, if it exists in my this array, it should be on the left-hand side of H here, right? Because my array are sorted. So if G exists, it should be here before the H. So what I do next, I need to change either start or end every time. Every time after you compare your mid with the target, if they are not the same, you either change the start or change the end. It's like to see, should you concentrate on the left only of your mid or on the right of your mid? Just like the BST, just now, if H is not G, is either I select to go left or go right. So based on here, I should concentrate on the left of H, right? Because G should be on the left. then I need to change my n. Means the boundary that I'm going to search now is within 0 to 6 only. And this part here, starting from index 7 to 14, I can totally ignore. Just like here, for my, if this is not clear, I just go to left of H, right? I don't go to the right of H. For binary search, also the same. Okay, I change my n to 6, mid minus 1. And then if I change my n, I need to calculate my new mid again, because now my boundary that I'm going to search in the array is from 0 to 6 only. So how to calculate mid? Use back the same formula. 0 plus 6 divide 2, you get 3. So my new mid is 3. So for this 3 here, the value is d, right? So I'm going to, every time when you get your new mid, you are going to compare with your target value. So when I compare with G and D, oh, they are not the same also. So this is not my target value, the middle element. But never mind. Then you decide again, okay, should you go to left of D to find G or right? Based on alphabetical order, G should be on the right-hand side of my D. So I need to change the boundary that I'm going to search now is within here only, after D until 6, right? So I need to change my start. You see? Just like here, after I compare D, or it's not like in BST just now, right? I have to go right. So when I change my start, right, I have to mid plus 1. So this is my new start. And I just concentrate on this part only in my array to look for G. This part here, I can ignore. I don't have to come here anymore, right? So now I have, because my start change, I have to calculate my new mid again. How to calculate? Use back the same formula. 4 plus 6 divide 2. Your new mid will be 5. 4 plus 6 is 10 divided 2 is 5. So when you get this 5, okay, your new mid again, F. I'm going to compare with the target again. And it's also not G, F is not G. Okay, then I decide again. If G exists, it should be on the right-hand side of F, right? So I need to change my start again. Mid plus 1, 6. You see? Okay. So when I change my start, I need to calculate my new mid again, right? Okay, now both my start and end also 6. So 6 plus 6 divide 2, you get 6. So your new mid is also 6. You see? So when you get your new mid, you compare with your target. So when you compare with the target value, you find that, oh, G, finally I found my target value. It's in index 6, and you return 6. The index where G exists in the array. Okay? So you see, this is how we perform binary search. It's very similar to how you search in the BST just now, right? Just like here, you search in the tree, but this one, all your data is stored in the array. So this is how we perform binary search in the array. Okay. So how do we implement this binary search? Okay. Okay, you see, okay, when I perform the binary search, I also pass in my array. I also pass in the size of array and also the target value, right? And I need these 3 variables, remember, my start and mid. So when you just call the function, means when you start searching, the area that you search is actually the whole array, right? Just now remember, I show you. So that's why your start value must be 0, and your end value is the last index in your array. Like in this example here is 14. So that's why because the array size here is 15, but the index we start from 0, you should minus 1. So it will be 14. And then the mid, okay, mid you need to calculate based on the start and end. The formula is given here, as you can see. Okay, since we are going to continuously search for the target as long as my array mid is not the target, I'm going to change either my start or end, right? Just now remember, to find my target value, we need a while loop. The condition is start less than n, less than equals to n. Means as long as the value of your start is less than n, actually your start should less than n, right? Or at most is equals to n. It's not possible that your start value is more than n. If this happens, it means what? it means the item that you find doesn't exist. So that's why you see your while condition, as long as it still start less than or equals to n, you will still either, means you are still searching in the array, okay? Then that's why you always either change your n or change your start, so that you concentrate on the left, on the right, right? And calculate the new mean again, okay? Until you find, or you either change your start or n, okay? When this condition becomes false, means that you still cannot find, you still cannot return the mean, means this item doesn't exist, okay? And you return -1 at the end, see? But when we just start, okay, I will calculate my mean based on my start and end value, like just I show you, like 0 plus 14 divide to 7, right? So array 7 more than array 7 will be H, then your target is G, for example, if I use the same example here. So is my H more than G? It's not true, right? My H, is it more than G? Yeah, it's true. If it's true, means that the array mean is not target, right? If it's the target, it should be equal. You will return mean already, right? So this if and else if is for the condition where the array mean is not equals to your target. So it's either you change n if your array mean more than target, like just now, you compare H more than G, yes, you change n. So you shift your n. How do you shift your n or change your n? Mean -1. Okay, because your mean is 7, -1 is 6. It's like just now, remember the second step, we change the n to index 6. So it's like you don't come to this part anymore, you just concentrate on the part from index 0 to 6 only. Okay, you change your n already, then you will come back to your while condition, you check again, oh, my start is still less than or equals to n. Then I calculate my new mean, right? Okay, then based on the new mean, then you check the condition again. Is it more than target or less than target? Or it's the same as target, means you find, then you return it directly. Okay, so this is the coding for your binary search. Okay, you can actually go back and try to play around, whereby if you really want to trace the program, right, what you can do, you can always print the value of start, mid, and end inside here, so that you will see how it changes your start, mid, and end, and also the array mid. You can see which is the value of your array mid. Okay, so you can check about, I mean, try this out. And then when you call the function, you can always change your target. Like in the example that I showed you previously here, we find G, right? But you can always change it to other values and see how your start, mid, and end change. And you can also try a target value where it doesn't exist in this array. And then from there, you see how it will return you -1 when your start value more than n already. Then you will terminate the while loop, and then you return -1. Okay, this is when you know it doesn't exist. Okay, so this is for the binary search. Okay, binary search. So for binary search, you can see that here, just remember when you want to use binary search, your array must be sorted. Now you see why the array must be sorted. If your array is not sorted, right, you cannot perform binary search. Because here, whenever we change the boundary where we want to search in the array, we assume that the array is sorted, right? If it's not sorted, you cannot be sure that it doesn't exist in the other part. Okay, so it won't work if your array doesn't sort, it is not sorted. Okay, so make sure it's sorted. And here, this example, this code here, we assume that the array is sorted in ascending order. Okay, if it's descending, then you have to change the symbol when you compare. Okay, then if found, we return the index of where the element, the target is in the array. If we cannot find, then we just return -1. Okay, so that when you call, you check what is the value returned back. If it's -1, you know it doesn't exist. Else, the value returned back will be the index of the target. Okay, so let's look at how do we look at the big O for this one? Because there's only one loop, right? We have just one while loop here. So the search time is at most order of n. Okay, if you really have to search for all, but this search, you only have to go through one external path only, right? So the search time is actually order of log 2n. Okay, log 2n means every time, just like binary search, is either you concentrate on the left or you concentrate on the right. It's like you, from one whole array, it's like you divide to two, then you just take one part, then you divide to two, then you just take one part, then you divide to two. Okay, so that's why it's order of log 2n. Okay, for binary search. So if we compare this linear search and binary search, these two types of searching, right? You can see that here we compare according to worst case scenario. Worst case scenario. So worst case scenario for linear search, it will be order of n, right? If let's say you cannot find the item. Same also for binary search. If you go and search, you cannot find it. So for linear search, it will be order of n. It's a linear growth rate types. How it depends means that how the time taken grow when your data size increase is linearly, because you have one for loop. You need to execute or check all the elements, then only you know for linear search, right? For binary search, is only at most log 2n. Logarithmic. Okay, so from here you can see that binary search is actually more efficient than linear search. Okay, in terms of worst case scenario, if you say that when your data size increase, actually binary search is more efficient compared to linear, because you don't really have to go and look for all the, what you call it, check every element. Okay, for the binary search, you always concentrate on either left or the right. Okay, to search for what you, for your target value. But linear search is you compare one by one, starting from the first one until the last one, if it doesn't exist. Okay, but then can we have a better searching algorithm? Actually, yes. Okay, so far from linear search and binary search, the best searching time is log 2n, right? Which is from binary search, right? Okay, we can actually speed up the searching time to just order of 1. Order of 1 means what? If you really have order of 1 means this searching doesn't depend on your data size, you see. It is very fast. No matter how many data you have, when you want to search for something in this data, it's order of 1, the same time, the same number of, you can say, number of time to search for it. Even you have 10 items, or you have 1,000 items, you have 10,000, 100,000, you have 1 million items also, the time it takes to search for something is the same. Then this is very good, right? Okay, means that your algorithm doesn't depend on the data size at all. Okay, so this can happen if we can use something called a hash table. Okay, for example, so let's say what you can do, you can create a 1D array of size n that to store, let's say, n personal record, where every record you have a unique ID. Okay, every record you use a unique ID to store. So let's say your record ID I, it will be stored in this location in your array ID I. Okay, so when I want to search for something in this n record, I want to search for a particular record. Okay, I will go to this table. How do I go to this table? I just go to the position array IDI. Okay, means that just go to that location only and search for it. The other location you don't have to go because it won't be there. So you can see if this can happen, the searching time is actually order of 1. You don't depend on data size at all, because you just go to a particular location to search for it only. Even binary search, you still have to go to a field, right? One external path, right? But this one, you don't have to. After you know what is the ID, just go to the position. That's it. Okay. So, but of course, in some application, it really depends on what you store. It can be names or it can be some other values. Okay, so you can use a function to generate this ID. If let's say, for example, what you want to store is a name, we don't really have the ID number, right? But you can use or create a hash function to pass in the name, and then it will give you the ID. Okay, this name should be stored in this ID. So whenever you want to find this name, you just go use back the same hash function, and then it will give you the same ID. Then you just go there and look for it. Okay, for example, conceptually, in diagram, this is how it works. Let's say this is your hash table. It's just like an array, where every element here you store one of your key. Let's say the key is the data that you want to store. Okay, it can be number, it can be name, it can be anything, any data that you want to store. So you want to store inside this hash table, which is actually array. So what you do, you don't directly go and store like wherever you want. First, you need to come up with something called hash function. Then you send the key, the data you want to store, to this function, and this function will return to you the position or the index where you should store this key in this hash table. If the position is 2, then you will store the key here in index 2. If the position that come out from the hash function is 5, then you store in index 5. Okay, so that's why this is how you store the key, right? Now, when I want to search for this key, let's say, okay, the user say, I want to search for this key. Then you will send this key or the target that the user want to find to the same hash function, because based on the same formula, you should get back the same position, right? If when you store that timer, this T1 is stored in position 2. So when you search for T1, you send to the same hash function, it should also give you back position 2. So you just go to this index 2 to look for this T1. Okay, if you cannot find it here, means this T1 doesn't exist. You don't have to go to any index to find. It won't be there. Okay, but if it exists, you will find it here when you go to index 2. Okay, so that's why you see why if you store the data in hash table, you can achieve big O notation of order 1. Okay, so how do we choose the hash function? There are 3 types. You can use truncation, folding, or modular arithmetic. Let's look at each one. Truncation is very simple. You just ignore part of the key and use some of it as the index. For example, if your key is a mixture of 8 alphabet, you have digit, and let's say your hash table, you have 1000 location. So what you can do, you can just take 3 digits out from a certain position in your key as the index in your hash table. For example, this is one of the data you want to store, one of the key. You have 8 digits, right? So you decide, okay, I will take the digit in position, let's say 1, 2, 3, 4, 5, 6, 7, 8. 4, 7, and 8. So this key will be mapped to index 594 in my hash table with 1000 location. Okay. Conceptually, okay. So this method is very fast, right? Because you don't need to really compute anything. You just take the digit from a certain location in your key as the index, just like you just retrieve only the certain location here, and then you get your index. Even though it's fast, but it failed to distribute the key evenly throughout the hash table, which means if you have another key P71, let's say you have another key P 5, 3, then 5, 9, 6, then 9, 4. So you see the second key, the position, the digit in the same position is also 594. So then it will be mapped to the same location. And then when you have more than one key mapped to the same location in your hash table, we call this as collision. You see? And then it's not distributed evenly, means that you might have some key mapped to the same location, and then some location in your hash table will be empty. Then it's not distributed evenly, then this is not good. Okay, later I will show you what is collision and how do we solve it. Okay, then the another example for truncation here. is, okay, instead of taking just the 3-digit from the key, what you can do, since we have this alphabet here, we can also use the alphabet. So Q59, let's say this is how I extract this 3-digit from the key. And then Q, if I use hexadecimal to represent is 51, then I can either use 5 or I can use 1 as the first digit. So means that this one can be mapped to 559 if I choose 5, or 159 if I choose 1. You see, you can also do that. Okay, so this is example of how you can use truncation or digit extraction, okay, as your hash function. It's very fast, but you might not store the data evenly throughout your hash table. Okay, it's possible that you have a lot of collision occur, okay, if you use this method. Okay, the second method is called folding. Folding here, okay, for example, if this is my key, what I can do, I separate this key into 3 parts, 625, 38194, and then add it up, I get 1100. If let's say my hash table have 1000, 1000 index, right? So 1100 exceeded the index, right? So what I can do, I can truncate it to 100. If this is what I get, then this data will be mapped to index 100 and stored inside the hash table, right? So this folding is actually better than truncation just now, because you will use every part in your key to generate the hash value or the index value, right? So the possibility to get the same index should be lower. The probability should be lower compared to truncation just now. Okay, but still it's possible to have collision as well if you use folding. Okay, then the last method that we can use is called modular arithmetic or modular division. So for example here, this is an example of using this method. Let's say my key is actually a string or a name that I store. Then what I do is, if this is a string, right, I can use each part of the string, each character, I should say, of the string to generate the hash value. Okay, for example, this is one of the formula that we come up with. You can have your own formula. This is just one example. Okay. So you see, after this while loop here is where I take each character in my key, okay, to generate the value. So this value that I get at the end, right, I will modulus it with the size of my hash table. For example, let's say my hash table here, I just have 7. The size is 7. So I will modulus with 7 so that the value or the index I get is from 0 to 6, right? It's within the size of my hash table. Okay. So let's see this method, the spreading means that whether it can distribute evenly throughout your hash table or not. It depends very much on the modulus that you choose. Means that the size of the hash table. Usually don't use small integer. Okay, here I use 7, which is small, because I want to show you the example later in the coding. So that's why I use smaller. But usually try to use, of course, a bigger value, okay, for your modulus. And if you can use a prime number, it will be better, so that less key can be mapped to the same location here. Okay, and this method can achieve a better spread compared to the other two. Okay, so when you have a better spread, means that your data will be stored evenly throughout your hash table. Okay, so let's look at an example. Okay, how do I use the hash function just now to store to generate the hash value, or the hash value at the end is actually the index where I should store this name or the key. Let's say the name I want to store is Aho, okay, or this is my key, right? If I use this value to generate the value here, okay, let's see. Because here S is this string, right? So I will go through every character in the string. That's why here my formula is Si plus 3 multiplied value modulus 7. So when you use a character with what you call that, arithmetic operator, right? Automatically it will use the ASCII value. So uppercase A will be 65. So 65, okay, the first value I get, because this one will loop continuously and go through every character, right? So the first character A, 65 plus 3 multiply 0, modulus 7, you get 2. And then this value, it will be sent to the next loop when you go to the second character. Second character H, the ASCII is 104. So you use the same formula, then the final value you get is 5. And then this value will be used in the next calculation for O, right? And then finally, the value you get is 0, right? So if you use the same hash function to generate the hash value for each of these key here, this should be the hash value that you get. So for example, this AHO, the hash value is 0, means that this name should be stored in index 0 in your hash table. And then Horowitz, you get 5, right? The final value. So Horowitz will be stored in index 5 in your hash table. And then Nov, index 1, Cruz. Now when it comes to Cruz, you see it's also index 5, right? This is what is collision. When you have more than one key, right, map to the same index in your hash table. So how do I store Cruz? I have already stored Horowitz here. So this is what we call as collision. How do we solve this? If I just use a 1D array, this one cannot, definitely, I cannot store Cruz here, right? Because one element I can, you can say one element in your array, I only store one data, right? So I can solve collision using chaining. One of the example is to use chaining. Chaining here means in my hash table, right? Instead of storing the name directly inside every element in my hash table, I will store a linked list. Remember linked list? So I'm going to store a linked list, okay, in each element in my array. So now, this is how I store, right? Just now I hold in the first index, Nov in second. Now in the fifth index, I store Horowitz. And then when it comes to Cruz, the second one also 5, right? Doesn't matter. It's like I just add one node to this linked list here in index 5. So this is how I can store 2 nodes by using a linked list. This method is called chaining. Okay, it's called chaining. So you can see if this is how I solve collision, right, using chaining. The worst complexity, means when I search for something, the worst case complexity for hash table with chaining is order of n. When will this happen? Worst case. When if you are really so unlucky, the hash function that you use, all the data that you hash is mapped to the same index. Then all your data, you have n data, right, will be stored in this linked list in index 5, right? Which I think usually it won't happen unless you are so really unlucky. How come you can use a hash function that can hash all your data to the same index, right? Okay, so this is worst case scenario, but worst case is also order of n, right? The best, of course, is order 1, where your data are spread evenly, like each one you store one name, one or two. So like even this one too, when you want to search for Cruz, it will be hashed to index 5, right? You just come to this index 5, you just traverse the linked list here to look for Cruz. Okay, like if you have 2, it won't be, you won't traverse, or it won't take you long to find Cruz. Okay, so average is also still order of 1. Okay. So what we do now, if we use chaining, we use linked list at each position in your hash table. Okay, then it's up to you whether you want the linked list that you store in every index here, if it's sorted or not. Okay, so at each position, this is how it looks like. You have a linked list, then this 0 here will be the size of your linked list. If it's 0 means you don't have any key map to this index in the hash table. That's why your linked list here is an empty list. That's why it's 0. Okay, and conceptually, this is how a hash table using chaining looks like. Okay. Okay, if based on the hash value that we get for each of the name just now using the hash function, and I use a link a hash, I want to store in a hash table using training. This is how the hash table will look like. Like for example, in AHO, store in index 0, right? So here my linked list only have one item. The second one, the index, you can see here Langsam and Sedgwick is the hash value is 2. So that's why these two names will be stored in the linked list in index 1. Okay. Sorry, index 2. Index 1 is Noof and Standish and Noof, right? And this is the size of your hash of your linked list. So when you check out, if you see that this is 0, it means like index 3, the size is 0, right? Means that this linked list is empty, which basically means we don't have any name that is hashed to this index 3. Okay, so this is how a hash table with chaining looks like. We basically store a linked list in every index here instead of just storing the name inside. Now, let's look at the implementation of this hash table. If I want to, my example is using the same hash function that I showed you just now with this same value here. So this program will be given to you. You can refer to the whole program yourself, but you can look at the part by part here. So at first, to represent the hash table, I create a struct called hash table. Then I have I create a linked list, because remember, in every index in my hash table, I'm going to store one linked list, right? So this table is my linked list, the name of the linked list. Okay, I have this table here, list table, and what I store inside every element in the linked list is constant, which is a C string, basically to store the name. And then this total element is the size of my hash table. So when I create the hash table at time, then I can specify if I want it to be size 7 or size 10 or size 100. Okay, so I can choose. Then this is my hash function that we've seen just now using the same formula. Okay, and inside the struct hash table, okay, I also have this function, the constructor, where I will call when I generate the hash table. It will help me to initialize my hash table to the number of index that I want. And inside my hash table, every index, I will store one, what you call that, one linked list in every element. So you can see this is my array table. If my total element is 7, that means I create an array of 7 elements, and every element will store this type, list constant character asterisk, which is a list that store a string in every node. Okay, then I also have a function so that I can use this in called insert element to help me to insert what you call that, every name to my hash table. First, of course, I have to go through the hash function to get the index. Then I will use, because here I use the STL list, you can see. So I use the function pushback to insert this key to my hash table here. Okay, I hope you still remember if you have come for the first workshop, the STL list, we have this pushback function, right? You can refer to the first workshop material. Then I also have this remove element function to help me to remove a key from the hash table if I want to remove. So I will call. So how do I do that? First, you also have to get, based on the key, go through the hash function so that you know this key will be stored in which index, the X. Then you go to this index in your hash table. If it's empty, if your list is empty, that means your key doesn't exist, so you cannot remove. So what you do, just return false to say that this key doesn't exist. Else, if it's not empty, need this part here, which is means that inside this index you have a linked list. Then because the linked list can have more than one item, so that's why you need the iterator, because it's a STL list, to go through starting from the first node and check whether it's the key that you're searching for or not. It's like just now you have Langsam and Proust, right? So you want to find Proust, so you have to go through the list. Like you compare Langsam or not Proust, then you go to the list Proust, then you find. Okay, so when you find the key, then you erase, you delete. Okay, and then return true, means you successfully remove. Else, if let's say when you go through the list, but this item doesn't exist in the list, which means the item also doesn't exist. So you also return false here at the end. Okay, this is remove. To search for the element, a particular name in your hash table is quite similar to the remove. Okay, where you also have to send the key to the hash function to get the index, then check if this index, the linked list is empty. Here I return -1, because when I search element, I want to know if this key exists, it exists in which index. So I return integer, which is the index. But if what I return is -1, which means this key basically doesn't exist. Okay, then this part here is to go through. If let's say this index contain a linked list, then I will use this part to go through every node in this linked list to find the key. If I can find, then I return the index. Else, if I cannot find, then I return -1. Okay, this is search element. Then I have another function called the print off to help me to print the content of my hash table so that I can see what I have in my hash table. So I have, this is how I do it. I will go through, I have one for loop here to go through every index in the hash table. Depends on how many index I have, the total elements, right? Then for each element, I will have this for loop to go through the list that I store inside the element. Okay, and then I see out each name. The J is the name. You can access like this if you use the STL list to go through. It's like to go through every node in your list. Okay, this is like a short form. Okay, so based on the hash table that we create just now, this is what I should get. If I call the print all, this index 0 Aho, Node, Standish, index 1. Index 2, you have Langsam and Sandwich. Index 5, you have Horowitz and Cruz. For those that don't have, we don't print anything. Like in index 3, 4, and 6. We don't have any name map to it, so that's why it's empty. There's no list inside. The list is empty. Okay, I should say. Okay, then the main, okay, how do I use this struct hash table that I create, right? So in the main, when I want to create a hash table, I call hash table ht7. Okay, means 7 indexes. Then this is the name that I want to map or hash or store inside the hash table. Then I will call the insert element to insert this name 1 by 1 to the hash table, right? And then print the hash table using the print all. After that, here, okay, I also use the search element function to help me to search for a particular name in the hash table. So if it exists, like Horowitz, it exists, right? It will tell me it's in index 5. But when I search for James, which doesn't exist in my hash table, right? So it will say that, oh, James doesn't exist because it returned -1. Okay. This is the sample output for this part. Then for the last part, I remove element. Okay, initially I have Cruz, right? Which is stored in index 5. So if I want to remove Cruz, I will just call the remove element, pass in the Cruz, and then it will go to the hash table, remove this, and then I print the hash table again. And now you see Horowitz, Cruz doesn't exist in index 5 anymore because it's removed. Okay, so this is an example of how I remove, how do we implement a hash table. Okay, I think we don't have a lot of time. Never mind, I have one last topic for the searching, which is an example. But this one, I just go through it. You can look at the program yourself later after it's uploaded. Okay, here we look at the problem of how to find a missing number. For example, let's say you are given a list of n-1 integer. And these integers are in the range 1 to n. And here that there are no duplicate in the list. And we know that one of the integer in the list is missing. So write a program to find this missing integer. For example, my input is 1, 2, 4, 6, 3, 7, 8. Assume that this is not sorted. Okay, very obvious here, we can see that 5 is missing, right? From the list of integer 1 to 8. So your program should output 5 to let you know that 5 is missing from here. Okay, you can refer to this program for the whole program. Okay, we have 3 methods that can help us to solve this, how to find the missing number. One is using brute force. Brute force is you just have to, for each number from 1 to n, like 1 to 8, if your n is 8, you just check whether that number is in the given array or not. Here you need to use 2 for loop. The first for loop, you go through each number from 1 to n. Then inside every time, let's say you start from 1, then you go through every element in the array to see whether this one exists or not. If it exists, you set found true. And then you break, then you go to I equals 2, then you see inside the array it got 2 or not. Okay. If finally you really cannot find, means that, oh, 5 I cannot find. Then I know 5 is missing. Then you return 5. This return -1 here, if something go wrong, like for example, the n value you insert is not valid and things like that. So that's why here we return back at -1. Okay. So the time complexity for this method, this algorithm using brute force, is order of n power 2, right? Because you have a nested for loop, you see. Okay. Okay, the second solution is you sort the array first, right? Okay, so to sort the, let's say assume that now when I call this second method, my array is sorted. So what I can do, if I know my array is sorted, I can just go through every element. I just have to, if I know that it's sorted 1, 2, 3, 4, then 6, 7, 8, right? So every time I just start from go through each element in array, and then if I cannot find a number in the array, like every time each element, array I, start point from 0, it must be 1, right? Array 1, it must be 2, right? Array 3, it must be, array 1, it must be 2, array 0, it must be 1, array 1, it must be 2, right? And so on. So if you find that this array I is not equals to I plus 1, means this I plus 1 is missing. So this is how we find out. But here, if what you are missing is the last element, or let's say 1 to 8, you are missing 8. Okay, then you need this part here to find it out after your for loop. Okay, so this is how the second solution or the second algorithm, how I can find the missing number. I sort the array first. Okay, and then I scan one time. And then this method, it only costs me order of n because I only have one for loop. Of course, if I don't consider the sorting process as well, okay. Then our solution is the best one. Okay, remember just now initially at the beginning, I told you to find the total for 1 to n. We use the formula, this one, n multiply n plus 1 divided by 2, right? So what I can do now is I can sum up all the elements in my array, right? I use this formula. Okay, I sum up, I know the sum already. Then what I can do, I just use a for loop and I subtract every element in the array that I have. So the remaining value that I have after the for loop in the sum will be the missing value. Okay, so this is another way that you can find the missing number. And this method is really cost you order of n because you only have one for loop here. And this is fixed one. It's constant, right? How to calculate the sum. Doesn't matter what is your n size because we use the formula. So you only need one for loop. So this way is better than actually our first two methods, the third solution. Okay, and this is the main function if you want to run. Here I create another array so that this is for solution 2 because we want our array to be sorted, right? So you can run through this method. You can try where here the missing number is 5. If you run, you should get 5. But of course, you can try different value. Like you try, okay, if the missing is 8, if the missing is 1 or any other number here. And you just run the program and see whether you get this or not. Or you want your array to be longer also can. Okay? Okay. So I think that's all for my part here because I think you need to go for your the preliminary test, right? Not the qualifying test. Okay. So I think I will stop here today. And I think you guys will go back to the main menu first. Okay, for the qualifying test. Okay, so thank you for listening today for the advanced workshop. And I hope you learned something, okay, from today's workshop. Okay, so I think you better go back to the main room. Okay, so I will see you guys. Okay, and good luck in your qualifying test.